Uh, Hello everyone, my name is Chen Liu Yi, and this is my presentation for the MAT 101 assessment. Today, I will invite you to look at the spaces between the numbers. We usually count with. We are all familiar with integers and simple fractions. But the true mystery of mathematicians lies in the world of irrational numbers. Today, my topic is infinite non-repeating decimals, like square root of 2. We will focus on this number. We can have 1.414 blah 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 blah. That is infinite, non-repeating decimals. To navigate this topic, I have broken my presentation down into 5 key parts. The first one is concept. We will define the difference between rational numbers and irrational numbers. Second, geometry. We will explore the fixed origin of these numbers. Third, I will mathematically prove why the square root of 2 can be not a fraction. 4. Approximation. We will see how we calculate these numbers if they go on forever. 5. The last, the insight. I will share an advanced perspective on the hidden order in choice. Let's start with the definition. We face a decimal dichotomy. On one side, we have rational numbers Q. Rational numbers are numbers that can be written as a fraction, like P over Q. We have terminate form like 0.5, 0.4, 1, blah blah. And we have repeat form like 0.33333, always 3. On the other side, we have irrational numbers. These numbers cannot be fractions. They have infinite lines. They have non-repeating pointer. The famous examples are pi, blah blah blah. E, the square root of 2. But where do these numbers come from? Are they just imaginary? No. They have a geometry origin. Please look at this unit square. By applying the Pythagorean theorem, we say that if the sides are 1, the diagonal D must satisfy these equations. And we get diagonal equals the square root of 2. These lines exist physically. You can draw it. But the ancient question was, can we marry it with a fraction? This question leads to the first crisis. Of mathematics around 500 BC. The Pythagorean believed all is number meaning everything could be expressed as a ratio of integers. However, a mathematician named Hipparchus discovered that the diagonal is incommensurable with the side. It was impossible to express it as a fraction. This discovery birthed the concept of irrational numbers. So, how do we prove a number mathematically that like square 2 is irrational? We can use the proof of contradiction. We can start it with a hypothesis. Assume that square 2 is rational. This means we can write the square 2 like a fraction p over q. We assume this fraction is in simplest form. That means p and q are complete. They share no common factors. Please remember that. Now let's look for our contradiction. First, we can square it. We can get 2 equals p squared over q squared, and we can get q squared 2 equals p squared. That's a 2. Oh, I can know p squared is even, and then p is even. Due to p is even, let p equals 2k. That means, we substitute p equals 2k, and therefore we back into the equations. Then we get 2k squared equals 2q squared. Then we get calculation. Then we can get the q squared equals 2k squared. That too, we can get q squared is even. And this one, we can get q is even. Let's see what we get. We found p is even and q is even too. Let's think. We know the p over q was in simplest form. They have not factors. But if p and q are both even, they both have a factor of 2. This contradicts our assumption that p over q was in simplest form. Then we can get a simple conclusion. The assumption is false. Square 2 is irrational. Since we have proven it is irrational, we know its decimals never repeat. We can never write it down completely. We can only approaching it. We can only approximate it. First, we know it is between 1.4 and 1.5. Then we can narrow the interval 1.41 and 1.45. Then we can zoom in infinitely close. Let's use the limited concept, but the digits will never set into a loop. Now, for an advanced perspective, we often say irrational numbers are chaotic because their decimals have no pattern. They are infinitely and non-repeating. But that's the perspective questions. If we say square 2 in decimal system, we can get this one, 1.41421356, blah 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 blah. No predictable pointer. But if we use a continued fraction, this becomes orderly. Like square 2 equals 1 plus 1 over 2 plus 1 over 2 plus 1 over blah blah blah. That's orderly. That's not truth, because we use a different perspective. And we can know Lagrange theorem. Quadratic irrationals always have periodic continued fractions like this. The order was there all along. Finally, how common are these numbers? George Cantor's discovery was shocking. He proved there are infinitely more irrational numbers than rational ones. In fact, if you pick a random point on number line, the probability of hitting a rational numbers is effectively 0 point. The probability of hitting irrational numbers is 100%. The universe of numbers is dominated by irrationals. To summarize, we explored the definition, the geometry origin, and the proof of irrational numbers like square 2, and we saw that despite their non-repeating decimals, they pose a hidden mathematical beauty. As the quote says, mathematics is the music of reason. That's the last. Thank you for watching.